we're not 100% clear on what the format's going to look like. So until I know what the format's going to look like, it's hard to say. Basically, if it is an online exam, and so it's a 3-hour exam, but say it's not a 24-hour exam, then it's the exact same aids, right? Like you can use your books, all that sort of stuff, but obviously you can't talk to each other. If it's 24 hours, same sort of story. If it's take home, things become a little bit different, because a take home exam would be like 8 or 9 days. And we have to be a little bit more careful about you using the internet and stuff, because obviously you can't not use the internet for 9 days. I mean, you might be taking other math classes, but we just have to be sort of careful about the things you look up in that time, right? So again, we've got 6 weeks until classes even end. So we'll maybe worry about that when we get there. And again, I've put the wheels in motion. I got to figure out what we are and are not allowed to do. And it's especially weird since we have like a mix of, it's weird because we've got a mix of in-person finals this year and online finals. Like I'm certain if we were, if campus was 100% online, I could get away with doing a 24-hour one without too much trouble. But because there's in-person things as well, the registrar's office is really, really picky about what you can and cannot do. So for example, last year, for example, Asun, and I think most of you know Asun, he wanted to do interviews, like kind of like oral exams, but I think technically a little bit different. So he wanted to do interviews for his finals. And the registrar was like, no, you're not allowed to do that. But it's not clear what is allowed to do and what you're not allowed to do, just because people can be really creative in how they want to do their assessments. So basically you have to go and you have to ask the registrar if you're allowed to do what you want to do, and then they can shoot you down, or they can say, yeah, sure, or they can say, yeah, sure, with these conditions. It's a whole big mess. And now that they've released the exam timetable, hopefully, they won't be as busy, but the registrar's office is pretty consistently like overworked, and they just don't have nearly enough people. But that's a thing. Okay, we're gonna see if I remember how to even write. So we're talking about sequences, and eventually series is basically going to dominate everything that we talk about for the remainder of the year. Functions, real functions are going to come back eventually, but for the next couple of weeks, we're really going to focus on sequences. So what is a sequence? Might as well just start with the definition. Okay, so a sequence is a map from the naturals to the real numbers. Is any function A from the naturals onto the reals. Okay. Is there anything we need to talk about here? Like that's literally the only difference, right? Here, maybe let me make my n a little bit nicer. So most of the functions that we've been working with, the domain has been the real numbers or some subset of the real numbers, but now we're looking at the natural numbers, right? Notationally, I guess maybe let's give an example. So for example, so let's say we take the function an is 1 over n squared, right? Then we might have something like a of 1 is 1. A of 2 is 1 over 4. 1 over 9. Right, and so on. So, and you might be like, okay, well, this doesn't seem like that big a deal. This is, a function from R to R, and we're just like plugging in natural numbers. Yeah, okay, that's totally okay. That's true. There are some functions which are sort of like more inherently sequences though. So maybe we could do something like, let's define another sequence B of n is, I don't know, let's do -1 to the n. Right, so B of 1 is -1. B of 2 is +1. B of 3 is -1. and so on. So this thing just, keeps flipping signs between plus and minus one. There is a real valued function, or a real function, which does behave like this at the natural numbers, but it's not like -1 to the power of x, right? Because you can't define that thing. That thing doesn't make sense. So there are some things that are more naturally sequences. Maybe here, let's do one more, just to give you an idea. So let's say C of n is n factorial. Yeah, this adds to, no. So I think the thing that adds to -1/2. Oh, yeah. No, wait, what adds to -1/2? It's the sum of, it's just the n, the sequence n, right? 1 plus 2 plus 3 plus 4. And that's actually just, it doesn't add to, or maybe that's -1/12. Whatever it is, you're talking about an analytic continuation of the Riemann zeta function, right? So, I mean, no, right? There's lots of, again, that sort of stuff where people in pop math kind of like dumb down something that's actually really complicated is, oh, no, I mean, like, yeah, it doesn't add to anything. You can make it mysteriously add to whatever you want. We'll talk about some stuff like this later, about how you can make these things add to weird things. This is an important point. When you do infinite addition, that's not a thing, right? There's no such thing as infinite addition. So you have to, like, the rules of infinite addition are different than the rules of addition. Does that make sense? So let's put it like this. When we did improper integrals were not integrals, right? They were not integrals. Integrals have to be defined on a closed and bounded set, something like the interval AB, right? And then we started suddenly talking about being able to do integrals of either unbounded functions or on something like, 1 to infinity. That's not an integral, right? It's an improper integral, and their properties are different. We have to prove, from scratch that the improper integral, for example, might be linear. We don't get that as a guarantee just because it looks like an integral. And it's the same sort of thing. When we start adding together infinitely many numbers, it's going to look like addition, but as a general rule, it's not going to behave like addition, right? And in particular, for example, commutativity of addition breaks. So, like, we have to be really careful. And there's a theorem which tells you when you are commutative, when addition is commutative, and you can move things around. And we'll talk about that. It's called the Riemann rearrangement theorem. But as a general rule, yeah, those things, infinite sums, are something that most people take for granted and don't properly understand. So it's just like, it's a little bit of a pet peeve for me because, again, pop mathematicians like to throw those things out there, and it often just clouds up the public discourse. I don't know, it bugs me. Okay, so n factorial is one that, again, actually there is a function which does do this, and I don't know if any of you know it. If any of you know it, please tell me. Do you guys know what factorial is? Just if I haven't, if I've written down factorial and nobody knows what factorial means, then there's an issue. Nice, Yvonne, very nice. Okay, so you're right, factorial. N factorial is you multiply all the natural numbers less than or equal to n together. So 4 factorial is 4 times 3 times 2 times 1. That's why we get 24. This, again, is something that is naturally a sequence, right? It doesn't make sense to ask what 1/2 factorial is, for example. Again, there is actually a function that does basically interpolate the factorial function. Does anyone know what that function is called? Right, exactly. Yeah, the gamma function. So the gamma function is a function which does do it. The gamma function is really, really surprisingly difficult to, when you write it down, it's quite tricky to define. But you'll probably have like an assignment question or something on the gamma function at some point in the future. It's a really cool example. Okay. Now, notationally, we often don't write these as functions. We don't use the function notation. So notationally, we write, okay, so instead of using the brackets, right, like a of n, that notation, we usually just write it as a subscript, right? So in the sequence A that we had above, we would write A sub 1 is 1, A sub 2 is 1/4, A sub 3 is 1/9, and so on. And then we would do B sub 1, B sub 2, B sub 3, so on and so forth. So we kind of changed the notation a little bit. There's still functions, but we changed the notation a little bit. And then when we want to refer to a sequence itself, we would write this. To refer to the sequence itself. Yeah, mathematically, we're often very lazy. And in that case, we kind of drop the n equals 1 to infinity. So sometimes, when it's safe, we'll just write a sequence like that, okay, in the brackets. And that distinguishes it, right? If I write just A1 here, this means an element of the sequence, right? But if you write the sequence in brackets, that means you're referring to the whole sequence, right? It's like the difference between a function f and the value of a function f of 1, right? Or even f of x. They're different things, right? So the brackets here help us indicate that we're talking about sequences. And for the most part, I'm actually not going to write the n equals 1 to infinity sort of thing. I'm going to drop that and just, when it's okay, just write down it in brackets. Now, some people, maybe let's just put this in blue here as an aside. Some people do sequences in angled brackets instead. So I've seen that, and that's okay. It's not kind of what I typically use, but it's nice because it can, sometimes you just got a lot of brackets hanging around and you want to use something a little bit different. So some people do use that. Have I ever seen square brackets? I don't think I've seen square brackets. It might happen. Basically, it's not standardized. Okay, so there are different people will use different things. Just be aware of that. Usually it's contextually obvious what they're referring to, though. Okay, any questions? Does that make sense? Okay. And you might say like, well, why do we introduce this alternative notation? And the reason is sometimes it is useful to think about a sequence as a function, but a lot of the time it turns out that's actually not useful. It's great from like a definitional viewpoint. It's great from a mathematical viewpoint, but sometimes you want to intuitively think about it in a slightly different way. And that way is as an ordered collection, an ordered countably infinite collection of real numbers, right? So when we write it this way, or maybe I should say like another way of thinking about it, of thinking about sequences. And frankly, this is kind of how I think about sequences. Another way of thinking about sequences is as an ordered, and that's important, and countably infinite collection of real numbers. Right? So in the above example with our A's, I just kind of think about it as 1/4. So instead of thinking about it as a function, I just think it's this ordered list of real numbers. And there have to be infinitely many of these, right? Even if they repeat, it doesn't matter. There are infinitely many of them. They're ordered because I can clearly distinguish between the third element of the sequence and the eighth element of the sequence. This sequence is actually decreasing, but of course they don't have to, right? Because the sequence B up here above goes from +1, -1, +1, -1, +1, -1, so on and so forth. So that's still ordered, right? But they don't have to be decreasing or increasing or anything like that. Eventually, we're going to talk about the limits of these things and whether or not they converge. But that's just that. This is the idea of a sequence. Okay. So, any questions about that? Is everything okay so far? Okay. All right. So that's the definition of a sequence, and we've got a couple of examples there. Let's talk about some properties of sequences, right? So I said, this sequence is decreasing, but I haven't strictly defined what that means. So let's talk about some properties. Okay, so if, and see here, I'm going to be lazy, if AN is a sequence, and usually we're lazy when we don't actually care, for example, where the sequence starts, right? It doesn't have to start at 1. If a set is countable, then it has order. Depends on what you mean by that. You can certainly put an order on it. But so for example, let's say, off on the side here, let's say I gave you the set 1, 3, 5. Sets don't have order, right? So these two things as sets are equal. And normally we'd be talking about infinitely many things, but as sets, these two things are the same because they don't have orders. But as sequences, it's like if I were to write down the sequence 1, 3, 5, ... that's different than the sequence 3, 1, 5, ... right? Because the order of the numbers therefore matters. And that's what we're talking about when we say it's an ordered collection of real numbers, right? Here, the first element of the sequence is 1. Here, the first element of the sequence is 3. Two sequences are going to be equal precisely when they have exactly the same, AN is equal to BN for all n, right? That's what it's going to mean. Right, yeah, exactly. So it's as a function, because its domain is n, it is inheriting, the sequence itself inherits the order structure from the naturals, right? But ordered, again, here means that one number comes before another. It can be, it depends on what you mean by ordered here, right? So there's a couple of different words. So an order is generally a relationship like less than or equal to, right? So certainly there is an order on the rationals. There's even an order on the reals. But when I say that a sequence is ordered, what I'm saying is that I know that A4 comes before A5 because 4 is less than 5. Do you know what I'm saying? I'm not saying, for example, A4 is less than A5. That's not true. But I'm saying that the order on the natural numbers, right, that 1 comes before 2, comes before 3, comes before 4, that order tells me that the order of the sequence elements matters as well, right? So that if 1 comes before 3, comes before 5 here, then 3, or on the other side, 3 comes before 1, comes before 5, just that order that you actually put the numbers in does change the sequence, right? So if you give it a different order, you actually are changing the sequence, just like you're doing it as a function. Yeah, exactly. The index is ordered. Yeah, maybe that's a good way of thinking about it. The index is ordered, and that ends up, if you want to remove the function description of a sequence and think of it just as a collection of numbers, every one of these numbers has to be indexed, and that index is ordered. Okay, cool. Yeah, so that's kind of like a good point. And again, we're kind of overriding or overloading the word order here, right? And we do mean the same thing. We do mean like the order on the natural numbers, but it's imparting an order onto the sequence, right? Which isn't an order itself. Okay, so if AN is a sequence, we say that, so I'm going to I really need to do like 8 definitions here. So I'm going to be a little bit lazy in how I do it. So we say that AN is bounded from above. Okay, and I'm going to define below at the same time. Okay, so it's bounded from above and then in brackets below. if there exists an m in the real numbers such that an is less than or equal to m, and then in brackets here, for all n in n. Okay, so again, hopefully you guys remember how to read this. If you want to say bounded from below, then replace everything with brackets, right? So you're bounded from below if an is bigger than or equal to m for all n. We say an is bounded if it's bounded from above and below. Okay. And there is a definition, a different definition of bounded that we've sort of seen with functions, right? But they're equivalent, right? These two definitions are equivalent. Does everyone know what the other definition I'm talking about? Like if you had to guess, so in this definition, there's some, not necessarily limit. It's funny, those two things actually are related. So here you're bounded from above and below, but your upper, exactly, Nicole, yeah. So your upper and lower bounds could be different, right? And as Nicole points out, is that like, if you want to actually use sort of the same bound plus m and negative m, you could do that as well. There exists m greater than 0. Like that. So this is a good little exercise. It's pretty straightforward. It's pretty easy to do. But if you want to just get your hands, dirty a little bit playing with sequences, prove these are equivalent, right? Prove that you're bounded in the red definition, if and only if you're bounded in the yellow definition. Okay, it's a good little exercise. Should be quick. It's really not tough. And we're going to have a different one here as well. So here I'm going to define increasing and decreasing. So an is, let's be very precise with our language, is non-decreasing, non-increasing if for all n and n. Okay, so it's non-decreasing, non-increasing if, again, sort of typically what you would expect is true. And again, these definitions are, we have these definitions. We know what it means for a function to be bounded. We know what it means for a function to be non-increasing and non-decreasing. And these are exactly those definitions, right? Like this isn't anything crazy. And of course, we have it is strictly increasing / decreasing. If an is less than an plus 1. For all n and n. Okay, and actually you might disagree. You might say, like, if I were to write what this means as a function down, this is actually not the definition of increasing as a function. At least not for, when your domain is the reals. So write that down. There is an alternative definition, which is equivalent. Can anyone think about what it is? And maybe let's say this red definition that I've given you only works because the domain is the natural numbers, right? If our domain was the real numbers, this obviously wouldn't work. So we needed a different definition. Can anyone think about it? Mm-hmm. Yeah, exactly. Yeah. So we'd say something like an is non-decreasing And this is probably more in line with what, we remember from functions on the real numbers. Okay. Yeah, Jinjin, exactly. So this is in this case, the yellow definition is probably what we're more comfortable with. An important thing, this is a really good exercise, and I really do recommend that you do this. Because our domain is just the natural numbers, we can use this thing of just relating one point to its next point, right? An to an plus one. We can't do that in the real numbers because there's no next real number, right? If I give you pi, we don't know what the next number after pi is because there are infinitely many. It's and not just infinitely many, it's actually dense and complete, right? So we can't do that when our domain is the real numbers, but we can do it with the naturals. And so this is a really good one. Again, it should be very, very quick. Prove that you're non-decreasing in the red definition, if and only if you're non-decreasing in the yellow definition. And you don't have to do all four. You don't have to do non-increasing, strictly increasing, strictly decreasing. Once you've done one of them, they're all the same, and you just replace the less than or equal to sign by whichever of the other three signs you want. So give it a shot. This is a really good one to make sure that you're comfortable with. Let's do an example. So let's say show that what is this? This is bounded for sure. Is bounded. And I'm pretty sure this is strictly decreasing. No, strictly increasing. Okay. Now, a lot of the strategies, because you can imagine you could have been asked to do a very similar thing about this function on the real numbers, x divided by x plus 1. And yeah, it turns out some of your strategies there will also work. Some of them won't, though. So let me kind of give you an idea of something that you can use to prove this if you don't know that it actually comes from a function on the real numbers. And then we can maybe state and prove a theorem about that, about what happens if it does. Okay, so we want to show it's bounded. This one's pretty easy. So we know for all n in n, this is true, right? And I'm just going to divide everything here by n plus 1, which is positive and therefore won't change the sign. Right? And that tells us an is always between 0 and 1, so it's bounded both from below and from above. Thus, an is bounded. And of course, again, if we use the definition that Nicole suggested, the yellow one, I would have to actually bound this between plus and minus 1. And of course, we believe that's true, right? That's, if you're bigger than 0, you're definitely bigger than -1, but whatever, right? Like these two definitions are equivalent. Use whichever of them is convenient for you. And in this case, it was easier for me to bound below by 0 rather than -1. It's all the same. Okay, so this is certainly bounded. Next, we want to show strictly increasing. So the way that we would normally do this with functions of real numbers was to look at their derivatives, right? And if you could show that its derivative was always, say, strictly greater than 0, you'd be in the money. And in fact, x divided by x plus 1 is actually strictly increasing as a function. And that will, because the sequence is defined from that function, we would get that to be true as well. Isn't it approaching? No, it's approaching 1. So if you think about it, when n becomes very big, n and n plus 1 are basically the same number, right? So when n is 1,000 and the denominator is 1,001, that number is basically 1, right? It's like 0.99999 something. So as n becomes very, very big, the difference between n and n plus 1 becomes like matters less and less. So the numbers are actually, well, here, let's do it. Let's see, maybe I'm wrong. But yeah, it should be approaching 1, right? Because the numbers are basically the same. So here's what we're going to do. Okay, cool. So there's a couple of things you can do this. I think a good way to do it is as the follows. And of course, this does not work for functions of real numbers. So for increasing, so for strictly increasing, let's look at an plus 1 minus an. And again, right, obviously you can't do this for real numbers. So this is going to be n plus 1 divided by n plus 2 minus n all over n plus 1. Let's give that a common denominator. What do we get? So we're going to get n squared plus 2n plus 1 minus n squared plus 2n, n plus 1, n plus 2. Almost everything cancels out. And we get that, right? So all I did was compute the difference between an plus 1 and an. And what I've managed to show is that when you do that, you get a number which is greater than 0, right? So what does that mean? It means an plus 1 is bigger than an. Okay, and voila. So this is a common trick, right? Just take the difference between an plus 1 and an, show that the leftover, the remainder that you get, is positive and is always positive. And that would tell you that you're strictly increasing. Another one comes up a little bit less often, but is still valid, is to actually look at an plus 1 divided by an and show that that number is always greater than 1, right? That would also give you strictly increasing. So another one which does come up sometimes, and it's going to come up for us actually a lot later. So another strategy. And of course, again, I'm using strictly increasing, but you can change the sign, do whatever you want. No, sorry, if I'm doing, yes, yeah, no, that is the right direction. Okay, sure. Or of course, you could do an divided by an plus 1 is less than 1. You could do that. Yeah, these are the things that normally work. Now you might say, okay, this is a pretty straightforward way of doing it. Sometimes though, you have much nastier functions. The benefit, I was kind of talking last time, right, about how we actually could start the course with this instead of finishing the course with this material. We could actually start with sequences because, you know, it's brand new material and we aren't relying on anything. The benefit of finishing the course with sequences is that we can use all of the stuff that we've learned so far in order to help us. So, you know, we have the following proposition. So, you know, if f, let's just say 0 to infinity, you can, some of you are going to start asking, do our naturals start at 0 or 1? My answer is, I don't care. Just whatever is more convenient for you. So if you want your naturals to start at 0, great. If you want them to start at 1, great. It doesn't make a difference. So if f is, and again, this is not a sequence, right? So because it's mapping 0 infinity, is a strictly increasing function, and we define a sequence like this, then an is also strictly increasing, right? And you're going to do that. You can check that proof yourself. Very easy, right? This is a one-liner. Very, very easy. But nonetheless, very powerful, because what we could then do, so another strategy to attacking this example above is to say, look, this looks like the function x divided by x plus 1, but we've only just plugged in natural numbers. So now I know that function is actually differentiable, right, on 0 infinity. So if I can prove that that function is strictly increasing, say by looking at its derivative and showing that its derivative is always strictly positive, then I can get the result for free, right? I don't have to do any more math other than computing a derivative. So same sort of thing. If you want to use that, you absolutely should. And this is going to make your life easy, because if I asked you something like, if I said show that the sequence n squared is strictly increasing, you'd say, well, this is stupid. It's obvious that it's strictly increasing, right? But you'd actually have to prove it. And the proof is, involves a little bit of work. It's not super trivial, but it's not that bad. Or you can say, look, this thing comes from x squared. We know that x squared on the naturals is strictly increasing, on zero infinity rather, and so we're done. What do you mean? How can they be equal? No, sorry. I'm not saying they're equal. I'm saying we're defining a function or defining a sequence. Yeah. So here, let me maybe rephrase it. Strictly increasing function. And we define a sequence for all n in n. Right? Or if you want to, alternatively, and this is a great other way of saying it, Sophia, it's like if you have a sequence whose values agree with a strictly increasing function at the naturals only, then you can conclude that that sequence is strictly increasing, right? So it's not saying that the sequence is equal to the function. You're right, that's not possible. But it's saying if your sequence agrees with the function at the natural numbers and that function was strictly increasing, then you're good to go. Okay, so again, this is powerful because any function that we know is strictly increasing automatically now gives us a strictly increasing sequence. And of course, same sort of thing for non-decreasing, strictly decreasing, and whatever, right? Whatever one I miss. So the strictly increasing here isn't important. The point is that you as a sequence can inherit whatever you get from your function. Now, an important point to this is the converse is not true. Right? The converse is definitely not true. Okay. It is very easy to construct a function whose, if you look at only the sequence defined at its natural numbers, you get something which is strictly increasing, but the function itself is not strictly increasing, right? And I could write something down for you, but I think this will probably be more obvious if we graph it. Right? So what if I did something like, maybe I should have started this in the middle. Let me start this in the middle. Oh, I guess, no, actually I don't have to. I'm just drawing something, so who cares? Right? And let's say that the sequence points that you take are these ones right here, right? Here's 1, here's 2, 3, 4, and 5. Right? So you can see here, this sequence is actually increasing, right? The sequence values are getting bigger. Nonetheless, the function that it agrees with is not strictly increasing, right? So the converse of this direction is not going to be true. We really need that the function bestows its properties on the sequence, but the opposite you can't say anything about. If you have some property of the sequence, you don't know anything about the function that it came from, precisely because, as Chu-Yang kind of pointed out, the function is defined at so many more points that really anything could happen, right? And there's basically no fix to this. Like you might say, well, what if we add differentiability or continuity or something along these lines? Yeah, there's nothing you can do, just because the sequence captures so little of a function's data, right? like a sequence defined only on the naturals versus a sequence or a function defined on the reals, the function defined on the reals has so much more data than the sequence does. So you can't make any inferences whatsoever. Okay, does that make sense? And actually, this might be a really good time for me to tell you how to visualize sequences. So naturally, you can use this picture here, right, where you think of a graph. So to visualize sequences, a sequence, you can think of the graph of the function, right? As above. Now, this is great for when you want to do things like translate information that you know about real functions into sequences, right? This is a great geometric picture for if you're trying to say, what do I know about functions on the real numbers and how those relate to sequences? This is a great picture. Turns out, though, this is generally not the picture you should have, okay? This is generally a very dangerous picture. It is sometimes valuable, but this is dangerous. More generally, okay, what you should do is visualize the image of the sequence points. Okay, so let me give you an example of what I mean by this. So let's say, here's my real numbers, right? And let's say I take a look at the sequence. Does it called? Yeah. A strictly increasing sequence is still, a sequence that is strictly increasing, like as a function. Yeah, that's totally still true. Or maybe you're asking something else, Truyang, that I didn't quite understand, but like, yeah, you'd still call it strictly increasing. Like this thing above here is a strictly increasing sequence, right? It just doesn't come from a strictly increasing function. So maybe we can say it a different way. Every strictly increasing function on the real numbers gives rise to a strictly increasing sequence, but not every strictly increasing sequence comes from a strictly increasing function, sort of thing, right? Like maybe it helps to think about it like that. So what I'm going to do for you is let's try and visualize this sequence. Okay, just because I think I want it to sort of jump between from the left and right hand side of 0, just so we can really kind of see what's going on. And let me just sort of plot some points here. Here's 0, here's +1, and here's -1. Okay, so the way that I want you to visualize sequences generally, which is going to work better, especially as you get into higher level mathematics, because you won't just be dealing with sequences in R, you might be dealing with sequences in Rn, in Cn. Eventually, later in this course, we're going to deal with sequences of functions. So, the graph isn't going to work when we do that. So let's draw this. Yeah, let's do this in green. So what's the first sequence? A1 is just going to be -1. Right? So here's A1. A2 is a half. So suddenly I jump over here, and there's A2, right? A3 is -1/3. It looks like that's going to be about there. A4 is +1/4, which is roughly about, I haven't drawn this super well, but, this is going to look like this. And so to me, right, like I sort of visualize the sequence as it goes down, and I can see that it's starting to hone in on 0. And this is going to be important when we talk about limits. To me, this sequence looks like it's starting to, it jumps back and forth around 0, but it seems to be narrowing in on 0, right? It's getting closer and closer and closer. Right? And this turns out to be sort of a better way of thinking about sequences. So does everyone see like the difference between these two visualizations? Maybe, in fact, maybe let me graph this sequence using the other way of thinking about it, just so that we can really see what's going on here. All right, so we've got like 1, 2, 3, 4, 5, 6. And the graph of this thing would be like -1. Oh yeah, maybe let me label these -1, 1. So we had -1, +1/2, -1/3, -1/4, like that. Okay, so two ways of thinking about it. Of course, this actually does come from, a graph which looks like it's up to you to figure out what this graph is. But it does actually correspond to a graph, right? It looks kind of sinusoidal, hint, hint. But that's something for you to figure out if you want to. But yeah, these are the two ways you should think about it. Top way is better. Okay, top way is definitely much better, and is going to serve you much better if you are capable of taking that into higher year courses. Okay, so maybe let me write this down as an explicit exercise. Find a function from R to R such that this is true. And of course, you could cheat and just do it straight lines, but maybe try and find a differentiable one. Or let's say find a C1 function, right? Otherwise, you could use the straight lines. No, because -1 to the x doesn't work, right? -1 to the x is not a function, because otherwise, what's -1 to the power of a half, right? That would be the square root of -1. So we can't define that. So whatever is giving us this -1 to the power of n term, we have to be more clever about like what we choose that to be as the function. So the 1/x term, that's no problem. You can keep that. The -1 to the x, though, you've got to figure out how to translate that into a function. Right. And like I said, you actually could cheat if the only thing you wanted, yeah, and exactly sine, but you're going to have to, again, play with the input and the period of sine in order to make sure that you get what you want, right? Because it's probably, that sine of pi is what, 0, and then sine of pi over 2 is 1. So you're going to have to play with the period in order to make it oscillate in exactly the way that you want it to. But again, that's not hard. Like you all know, I think, how sine works, and you can see what the period of this thing should be. And you can doctor it a little bit in order to play around with it, right? So it's not hard to do, but give it a shot and see if you can do it. And it really just comes down to, can you find a function which simulates the -1 to the power of n, right? And that's all you need to do. And again, if you didn't want a differentiable one, you could just connect these things with straight lines, right? You could have some sort of like diminishing sawtooth function. And that would be continuous. It wouldn't be differentiable, but it would be a continuous answer. And you could totally do that. But often we do, when you want to do these things, you often want a differentiable answer so that you can use calculus if you have to, right? So generally, the definition of a to the x requires that a is positive, just because you don't want to have to worry about like what happens when you have -1, right? A negative number to an exponent. So we, for the most part, when we define the function a to the power of x, we demand that a has to be positive, right? And in fact, a good reason for that is, so if you have a to the x, right, what's the definition of this? Remember, this is e to the x. We're using log a, right? But log is only defined when its input is greater than 0, right? So this tells us a has to be greater than 0. Now you can do it, okay, if you're going and you're doing like complex analysis and stuff. In those cases, you can take log of a negative number, just like you can take the square root of a negative number. That will allow you to be able to define a to the power of x for things like negative numbers, for things like complex numbers. But you need to be working in the complex space in order to be able to do that. So for our purposes, we're just working with the real numbers. That base has to be strictly positive, right? Because this is the definition, right? This is how we actually defined it. And in order for this to make sense, A has to be strictly positive. Okay. So let me think about what I want to show, because we're coming up on break point here. So let me just see. I don't care about that. Okay, let me just do a quick definition. Give you something to think about on the break, and then we'll take a break. All right, so let me see how I worded this, because, right, okay. So we're going to talk about subsequences. So if an is a sequence, you know what? Let me use the function notation here, actually, and then I'll show you what it looks like in non-function notation. So if I give you a sequence, a subsequence is a choice, is any sequence of the form A compose N, where N is a strictly increasing function. Okay. And it's a little bit weird here because I'm writing here down like N as a function, but up until now, we've also been using it as like the input of our function, but that's fine because we've sort of done stuff like this. You've definitely done stuff like this in high school where you'll be like f of x, and then you'll write x as a function of t. And so you get this composition f compose x compose t, right? This especially tends to happen in things like physics. So that's fine. So a subsequence is any sequence of this form where n is a strictly increasing function. And this might look a little bit confusing, but basically what we're saying is we're choosing, while maintaining the order of our sequence, we're just going to pick out certain elements of that sequence and then throw the rest away. Okay. So from the level of a collection of real numbers, so as an ordered collection of real numbers, right? So we've got an as the original sequence. Something weird is going on here. Yeah, why is my battery dropping? Okay, anyway, I'll figure that out on the break. The original sequence is an. We create a new sequence. A subsequence is a new sequence. A sub n sub k of the same elements or let's say is a new sequence A sub n sub k, let's maybe say consisting of the elements of A sub n in the same order. Right? So if we have A sub n is, say, well, let's use one of the ones we had above, -1 to the n over n. Then we could do something like A sub n sub k is -1 to the n all over 2 to the n, right? That is a subsequence. Every single one, or actually, no, maybe it isn't. Let me double check here. Ooh, maybe it actually isn't. You know what? Let me get rid of the -1 just because I don't have to worry about it. And so let's just do 1 to the n, 1 over 2 to the n like that. Right? Yeah, because in the other case, all of the even powers would have been even. Right? Okay, so every number, we agree that every number of the A sub n sub k's, 1 over 2 to the n, is an element of the A sub n, and they must occur in exactly the same order, right? So if we look at A sub n, what do we get? We get 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, dot, dot, dot. If we look at A sub n sub k, what did we do? So we took this number, this number, this number, this number. Right? So you can see we preserved the order. We took some of the elements of AN. We didn't take all of them, but we took some of them. And we made a new sequence out of that. So that's what a subsequence is, okay? And that's kind of, I think intuitively, that's what you would think a subsequence is, right? I take the elements of the previous sequence in the same order, but maybe I threw some of them away, right? Like I wasn't worried about them anymore. So that's exactly what a subsequence is and how subsequence works. So I want you to think about that. What I also want you to think about while we're on break here is what should the limit of a sequence be, right? Like if we want to start thinking about limits, what should the limit of a sequence be? What should its definition be? Like in terms of, say, an epsilon delta E sort of definition, what would that look like? Okay, and see if you can come up with those things on your own. So let's go on our break now. And in that break, I'm going to try and figure out why my Surface is not charging. Stupid thing. And we'll come back in 10 minutes. So I got 10:07 basically by my watch. So we'll come back at like 10:17. And then we'll basically talk about limits of sequences. Okay, so I'll see you all there in 10 minutes. All right, so I'm going to resume the recording here. We'll get started with the math stuff. All right. So let's talk about limits now. So this is subsequences, and it's really, really important. Like you might be like, okay, well, we haven't talked a lot about subsequences. Let's not worry about them. Subsequences end up being super important because often you can study a sequence by looking at its subsequences. And in fact, there are some very important mathematical properties that, believe it or not, are defined in terms of a sequence. There's a special property of something called compactness. And I think I can't remember if we talked about compactness in like December or whatever the case is, right? But we talked about compactness. There's an alternative characterization of compactness that works in, I'm trying to think of what it is. I don't even think it's Hausdorff. You might need like Hausdorff and paracompact or something. But so you have compactness. A characterization of compactness is that every sequence in a compact set has a convergent subsequence. Now, we haven't talked about what convergence means, but here is a property of a set, right? This is a weird thing. Here's a property of a set that is defined by saying every sequence whose, the sequence elements are in that set has a subsequence which converges, right? So this might seem overly complicated, but this is a characterization of compactness. This is actually called sequential compactness. So from this viewpoint, understanding the relationship between a sequence and a subsequence ends up being critical. We're going to prove once we talk about limits and convergence that a sequence converges if and only if all of its subsequences converge and to the same limit, those sorts of things. So subsequences are actually really important. There's also, here's another weird thing you can say. A sequence converges if and only if every subsequence has a subsequence which converges, something like this, right? I'm pretty sure that's the theorem. There's a weird one where if you go the next level down and look at subsequences of subsequences, if those all converge, that guarantees your original sequence converges. Something like this. Like, it's madness. But basically, you can study sequences by using your subsequences. Okay, that's going to be important. We are going to refer to it throughout the course. So make sure that you're comfortable with it. I figured out the charging issue too. I have no idea why it wasn't charging. I just unplugged everything, replugged back in. Suddenly it starts charging again. Okay. All right, so let's do another definition. So again, hopefully you've all been thinking about what the definition of a limit should be. And if you, again, think about like the function definition, you'll see there's only one sense in which convergence makes sense, right? Like, we can't ask, does it make sense for a sequence to converge at the number 3? I mean, the sequence is either defined at, or like the sequence is defined at 3, there's no sort of limiting behavior. The only thing we can talk about is the limit as the index goes off to infinity. That's the only thing that makes sense. And in fact, if we go back and we look at our visualization picture up here using like graphs and stuff, we can see that, yeah, okay, you can take these, the integer points on the graph of a function. Again, what's the only way convergence is going to make sense? We're going to ask if this thing sort of has a horizontal asymptote, right? Or in this picture here, where we have our real line, we're going to ask, do our points sort of cluster around a common thing, right? Like that's sort of the idea there. Okay, so let me just, for comparison, let me rewrite down the definition of what it meant to take a limit as x went to infinity for a function, right? So if f maps R to R, we say, right, this is just review. So, if you don't even want to write this down, you don't have to. If for every epsilon greater than 0, there exists an m. Again, you can take this m to be any real number, or you can take it to be positive. It doesn't matter. Such that for all x in R, x greater than, what do I call it, m, implies f of x minus L is less than epsilon, like so. Okay. Now, the definition for a sequence is going to be almost identical, but we have to make a couple of small changes where appropriate. So let's write it down. Let's just kind of keep track about where those differences are going to show up, but it's basically the same definition. So this is green. So if AN is a sequence, we'll say that AN converges to a point L in R if for every epsilon greater than 0, right? Okay, we can't escape the epsilon. For every epsilon greater than 0, there exists. And all right, here's our first change. Maybe let me use a different color here. There exists an n in R, right? Which we compare to this, which just said, there was some number greater than 0. Here we're saying specifically, because we're working in the domain where we have to, not n in R, n in n. I'm going off about how it's different and then I screwed it up. Because we're working, our domain is the natural numbers, this is where our n has to live, right? So there exists some number, natural number, such that, okay, our next change versus this one, for every n in n, little n greater than big N implies a n minus L is less than epsilon, right? So it's basically the same. And the only thing we changed is where some things were real numbers, these now suddenly become natural numbers, right? Otherwise, the definition is identical. So in some sense, it's very nice because functions, of course, there are many kinds of limits of functions. We had horizontal asymptotes, we had vertical asymptotes, we had, limits, one-sided limits, we had limits, the limit as you approach 2, the limit as you approach 2 from the left, the limit as you approach 2 from the right, the limit as you go to positive infinity, the limit as you go to negative infinity, all those sorts of stuff. And we don't have to worry about that with the sequences. Sequences is only one real type of convergence. It's as n goes off to infinity. And in that case, it happens to basically perfectly coincide with what we know about functions going off to infinity, right? We just change the real numbers to the natural numbers wherever we need to. So this is the definition of convergence. Now, from a visualization perspective, again, you can go back and you can think about things in terms of the epsilon delta band. Here, maybe let me copy and paste these pictures up here. And then copy. So if you want, you can just go back, right? Instead of redrawing these pictures, you might just want to go back to these original pictures. What we could do, so you already, I think you all have a relatively good idea of what the epsilon delta picture looks like in the bottom visualization, right? In this case, it looks like the limit is approaching 0. So you've got some sort of delta band, or sorry, epsilon band. And then there's some point, maybe it's about here. And you know that for every point after that n, all of your sequence points are going to stay inside of that epsilon band, right? And that's exactly the same sort of picture that we had when we were talking about functions. Beyond some point, the entire function stays within that epsilon band. Now we're just saying all of these points live within that epsilon band. Again, though, this is a bad way of thinking about sequences. It's helpful sometimes, but it's not great. And I would prefer that you didn't think about it like this. So using the top picture, how do we think about sequence convergence? In the top picture, the band, the epsilon band now, just looks something like this. Okay, and we're saying beyond some point, in this case, n equals, like you can see my epsilon band in the bottom picture is not quite the same as my epsilon band in the top picture. I guess I should include A3 if I wanted them to look the same. My epsilon band in the top picture just says beyond some point, all the sequence elements live inside of this interval, right? Does that make sense? And that's sort of the better picture, is when you're visualizing a sequence in terms of its image points, a convergence is no matter what size epsilon band I put around my limiting point, what size of interval I put, eventually all of the sequence elements lives in there. Or maybe better yet, eventually all but finitely many of the sequence elements live in an epsilon band for any size of epsilon. I think that's actually worth writing down. So an, I guess I should write notationally how we write the limit converging. Okay, so we say notationally we write, okay, this one probably isn't crazy. You're like, oh yeah, okay, that's the obvious thing. But sometimes, and in fact, more often we use the following. And when it's obvious, we'll even drop the n goes to infinity part. We just write the sequence goes to L like this, right? And you might have noticed sometimes I even would write this for functions. And that's fine. Again, this is fairly universal notation. Everybody knows what it means. So that this is probably the notation we're going to use instead of using this clunky sort of limit thing that we've carried around for functions. Okay, so notationally we write this. And another way of thinking about sequences, note that an converges to L if for every epsilon greater than 0, the epsilon interval, or let's say all but finitely many points of the sequence live in the epsilon interval around L. So all but finitely many of the an live in L minus epsilon to L plus epsilon. Okay. And again, that's sort of your intuition here. And this intuition is going to serve you really, really well if you go and you do like general topology or 257. Okay, sequence converges if all but finitely many elements of the sequence eventually live inside of that epsilon band. Okay, that's sort of the important thing there. Okay, now we're not going to spend a lot of time doing examples. If there are any questions, please don't hesitate to ask. We're not going to spend a lot of time doing examples because we've done examples of these sorts of things before, right? So, for example, let's say show. I'm trying to think of whether or not I did this example for the real numbers. I don't quite remember, but in any case, let's do it. And if we're doing it a second time, great, whatever. Okay, so here is a sequence. And what you're going to see is the proof is almost exactly the same as the one that we would do if this were a sequence of real numbers. Now, of course, this isn't always going to work because sometimes, again, you'll be given a sequence and it can't be written as a function from R to R, right? In which case you have to kind of employ a different technique. In this case, we're pretty lucky. And our proof is going to be almost identical to if we were taking x to infinity of x over x plus 1. All right, so I can say let epsilon greater than 0 be given. And choose n and n such that 1 over n plus 1 is less than epsilon. Now, this is a little bit different. This is sort of the only difference here, and it doesn't make a substantial difference. So what we could have just said when we were working with the real numbers is basically let m be, such that 1 over m plus 1 is less than epsilon or whatever. And we could have gotten really as close to epsilon as we wanted to. Here, we're just saying, yeah, by the Archimedean principle, I know I can find a natural number that's smaller, such that 1 over m plus 1 is smaller than epsilon. I might not actually be close to epsilon. Like I might actually be, like there might be that gap there, but of course we don't care, right? As long as we're less than epsilon, we're happy. So this is really just a cosmetic change. versus saying let n be a real number such that 1 over n plus 1 is less than epsilon. This is really just cosmetic, but technically speaking, it's structurally a little bit different, right? Okay, so we're going to choose a natural number such that this is true. So if n is greater than n, then n minus L, so what is this? This is n over n plus 1 minus 1. Let's give that a common denominator, so we're going to get n minus n plus 1 divided by n plus 1, which is equal to 1 over n plus 1, which is less than 1 over n plus 1, which is less than epsilon. Right? Sort of like our standard thing there. You guys have seen this sort of proof, tons and tons of times. And I went straight to the final answer, but you can imagine if you were doing this as like a rough work thing, you would have worked this out ahead of time to get that it was 1 over n plus 1, yada, 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 right? We've done this a ton. I would recommend, if you just want to double check it, because especially if you're kind of having trouble reconciling these two things in your mind, just try the proof of this. If this were a function of the real numbers, right, not a sequence, if this was a function from R to R, and you want to show its limit is 1, because it does have the same limit, and just write down the proof and see how the proofs are different. You'll see that the proofs are almost identical, right? In fact, here is now a very good time for you to maybe postulate and prove a very natural theorem, which is if a function from R to R has a limit as x goes to infinity, then if you define a sequence using that function, it also converges, right? Again, maybe I'll write that down, but not prove it, because it's very straightforward. Good little exercise for you to try. So if f is a function such that the limit as x goes to infinity, f of x equals L, and an satisfies an equals f of n, then limit as n goes to infinity, an is also equal to L. Okay. Well, but okay, so these exercises are legitimately things that you should be able to do. And, I ask you to, so yes, you are going to get more exercises. These are legitimately really straightforward though. Okay. I really recommend that you all check them. This proof is basically the fact that, oh, okay, if you converge to the real numbers, why not just guarantee that like in this proof that I did here, where I write this down, when I choose a real number to do that, why don't I just choose a natural number instead? And now the proof holds for the sequence, right? So it's really, really easy. Really, really easy. It really should be like only 1 or 2 lines. It's very straightforward. Yeah, and again, converse is not true, right? So it's definitely easy to find a function like a sequence that converges, but a function which agrees with it might not. An example of this might be something like, so let's say the converse is not true. And here's maybe a silly example. No, yeah, it's one of those things that like, I believe, because I have a good feeling for where you guys are now, where you're like, okay, he says this, I don't see it right away, right? But the moment you go away and you open your notes from that part of the term and you start writing it down, it'll be one of those things that you're just like, oh yeah, okay, this is certainly true, right? And there's tons of that stuff in math. No, I promise you, because I've had that feeling a million times, right? Like you're reading a book, someone says, this is obviously this. And you're like, is it obviously that? And then you start writing it down, and you're like, oh yeah, okay, it is obviously that, right? But sometimes it's not until you legitimately start writing it down that it becomes obvious. So yeah, this is what I'm saying. Like this proof is quote unquote, it is obvious that this proposition is correct, but you might not see it until you start writing it down. But I promise you that the moment you start writing it down, you'll be like, oh yeah, these are the same thing, right? So it's just kind of one of those things that happens all the time in math. Don't worry about it. And it's usually, that's the correct use of obvious, right? Sometimes it legitimately is obvious. Most of the time though, somebody says obvious, what they mean is it's obvious once you start doing it, right? It might not be obvious now, but it'll be obvious once you actually start working on it. And so, I try and avoid that word, or that it's clear or that it's easy. I typically try and avoid those words unless I really mean them. Okay, so even if when I say those and you don't see it right away, you shouldn't take that as a feeling of badness. Every single one of those has a little asterisk beside them that is, oh, this is easy the moment you start doing it, right? Even if you can't see it in your head right now, the moment you start doing it, you'll be like, oh yeah, it's okay. Okay, so the converse is not true. I'm going to create sort of like a stupid counterexample that hopefully you'll be like, oh yeah, I mean, but there's a better function you could have chosen, but whatever. So let's take the sequence to be 0. Okay, legitimately, it's just the 0 sequence. So every single point is just 0, 0, 0, 0, 0, 0. This obviously converges, right? This converges to 0. Okay, now it's relatively easy to find a function, right, which agrees with this. You could just take the constantly 0 function. But the point is that you don't have to take the constantly 0 function. I could take a different function. So if f of x, so sine pi x also works, right? Then f of n is sine pi n is also equal to 0, right? Sine is 0 at every integer multiple of pi, but the limit of f of x does not exist. Right? It depends on what you mean by just use sine x and cos x. I mean, certainly, again, we could have done some sort of translation of cos x to make this work as well. But yeah, what do you mean by just use? Yeah, sure. Cosine works as well. Right? Anything sine can do, cosine can do, because one of them is just a translation of the other by, pi over 2. So, I mean, that's not strictly speaking a correct statement, but 99.9% of the time, if you can make it work with sine, you can make it work with cosine as well. Okay. Okay, I guess we should maybe prove some quick theorems. Let's call them propositions. Limits are unique. I feel like I did I prove this for functions? i.e., if an converges to L, and it also converges to M, then L equals M. I feel like I did. Yeah. So maybe I won't prove it then, right? So exercise. I think I wrote that in white. You know what this end up being? This is great, like practice for your eventual final exam, because it's probably been a while since you proved these things, right? Again, the proof of this fact is identical. I promise you, it's pretty much identical to what we did way back when in like October or whatever the case is. Now, in those cases, we might have been taking the limit as like x approached c or something like that. And here we're talking about the limit as n goes to infinity, but the proofs are pretty much the same up to those small changes. So you might not remember how to do this proof. That's totally okay. If you want to, you can go back, look at your notes from October, and yeah, and that's what we want, right? Is that everything converges to the exam. So you can go back and look at your notes if you want to. Alternatively, you can try and prove this from scratch, and I think that's probably a more valuable thing take a bit of time, try and prove this thing from scratch. And then if you get stuck, go back and look at your notes from October and, try and mimic that proof. That being said, there are a couple of ways of proving this one. So don't feel, if what you get disagrees with what we did in October, don't worry about that too much. But try and do this one from scratch, right? See how that goes. And then all the limit laws are true, which again, I'm not going to prove because their proofs are identical. But we need to state them. So if AN converges to L and BN converges to M, then, okay, and because we haven't seen, like, hopefully, well, I don't know, you tell me if this is clear. Right? Because it probably feels like a weird, you guys probably haven't seen this way of writing down sequences yet, where we do sort of the operation inside of the bracket. But, if you have any, if you're bothered by this, we can talk about it. Right? But your usual limit laws. So the sum of two sequences, the product of sequences, the quotient of sequences, they all converge to what you think they should. Maybe we should talk about this notation quick, just to sanity check that, when I write A, B, N like this as a sequence, well, what am I talking about? Well, I've got the sequence A of N, and I've got this sequence B of N, and they're both functions, right? So how do you write the product function? Well, you'd say AB of N is A of N, B of N, right? So that means that the sequence, like if we thought about writing this thing down, how would you write this as a sequence? You'd write it like that. All right, so that's why that notation makes sense, like why the operations seem to be happening in the brackets. It's because as functions, that's actually how you do, that's how you write these things down, right? That's how you write the sum of two functions. You write it as f plus g evaluated on x. You write it as f times g evaluated on x, right? And so on and so forth. And so if we take that function notation and translate it back into our sequence notation, this is how it should look, right? The thing inside the bracket is the function. I guess technically you might argue that there should be an extra bracket around it, but whatever, who cares? It's just notation. Nobody, I think, will get terribly upset at you if you use slightly different notation. If you want to write it as AN plus BN converges to L plus M, that's totally okay. No one's going to get upset about that. Okay, so what I might actually do then is, instead of doing any more proofs, because I've thrown a lot at you today, right? What I think I'm going to do instead is I'm going to write down how many theorems do we need to do. 1, 2, 3, 4 theorems. What I'm going to do is I'm going to write the theorems down, and you can practice them. And you can see if you can do them yourself. And I say this understanding that it's probably not going to happen because you have a test on Friday. And if you had to choose what you were going to prioritize, it's probably going to be the test, right? All right. So I'm going to write these down. We will prove these ones on Thursday, but if you want to try them yourself, you can. So proposition. So a sequence AN converges to L if and only if every subsequence of AN converges to L. Okay, so sequence converges if and only if every subsequence converges and to the same point. So that's theorem number 1. This theorem, which we've now seen multiple times, is the following. This is called the monotone convergence theorem. So if AN is increasing and bounded from above, then it converges. Sorry, let me say non-decreasing. That's the language we've been using, is non-decreasing and bounded from above. It converges. I think we proved that for functions. In fact, I think it might have been a term test question, right? I think I made you do that. Every convergent sequence is bounded. If AN converges, then AN is bounded, right? Which is certainly not true of functions. So this is, right, an important point. This is not true for functions from R to R, right? You can have convergent functions that are not bounded. By the way, there is a squeeze theorem for sequences. We're probably not going to use it, but see if you can state it. And now here's the most important one. Okay, so we're going to put a little star beside this because it's so important. So a function from R to R is continuous at the point C if and only if whenever AN is a sequence which converges to C, then f of AN converges to f of C. Okay, so this last theorem is the most important. It's surprisingly not that hard to prove. The forward direction is not too bad. The backwards direction is a little bit trickier, just because you might not think about the right thing to do. The answer is contrapositive the backwards direction. But if we think about what this theorem is saying, right, let's look at theorem star. A function is continuous if and only if it preserves convergent sequences, right? That's another way of saying this theorem. You are continuous at the point C if and only if whenever you have a sequence which converges to C, then the image of that sequence converges to f of C. Depends on what you mean by substitution. I mean, that's kind of like sufficiently vague that maybe the answer is yes, but in some sense, it looks like, remember, what do we say continuity is? It was like you could evaluate the limit just by plugging the limiting point into the function, right? The limit as x approaches C of f of x is f of C. You can just plug x equals C in. And in some sense, this feels very similar, right? I've got AN as a sequence converging to C, and I can just take that sequence and plug it into F, and the output also converges to f of C. In some sense like that, it maybe feels like you're just subbing in the sequence, right? Sure, so it's like this. So let's say I have a function. So let's say f of x is x sine x, right? And we know this function is continuous, right? This function is continuous everywhere because it's a composition of two continuous functions. So let's look at, the point C equals 0. Okay, so this function says if I have any sequence which converges to 0, then the image of that sequence converges to f of 0, which in this case is also 0. So let's take a sequence to be 1 over n, right? Which we know, right, 1 over n converges to 0. So because this function is continuous, we automatically know. So the theorem tells us that f of 1 over n will converge to f of 0, right? And if we translate this, what do we get? So f of 1 over n is 1 over n sine 1 over n will converge to f of 0, which is just 0. Does that kind of make sense? Right? So you can take a sequence which you know converges to your point of continuity, and then if you act f on both the sequence and the limit point, you get out something which also converges. Right? Maybe the interesting thing, maybe I should have chosen something that wasn't like, yeah, or this function is also continuous at 1, right? So we took c equals 1, then f of 1 is just sine 1, which is a weird number, right? And if we took a n to be, I don't know, what do we want here? Oh, yeah, here's our n over n plus 1, which we know converges to 1. Then that tells us f of an converges to f of 1. Or equivalently, that would be n over n plus 1 sine n over n plus 1 converges to sine 1, right? Yes, yeah. Continuity is very structure preserving, as long as the structure you're not preserving is differentiable, right? So this is a little bit hard to explain. So there are properties which are not derivative properties, right? So properties like sequential convergence, right? There was no mention of derivatives. There are properties like compactness and connectedness, right? Which we talked about in December, which don't have anything to do with differentiability. All of those things are preserved by continuity. But the moment you get properties that are defined in terms of derivatives, continuity isn't good enough anymore. And that's not surprising because we know that there are continuous functions which are not differentiable, right? But continuity will preserve the things that occur, the structure and properties that occur prior to differentiability. And there's a reason for this. It's a topological reason. And if you're interested in pursuing this, we'll talk about it a little bit more in 257. If you take specialist topology, you'll learn about it there. But basically, continuity is a topological property. It's not an analytic property. And the fact that we just happen to talk about it in the context of analysis is like great, but continuity is actually more fundamental than that. I think most of us think about like continuity as being a precursor to differentiability. In fact, they're totally different. And continuity is its own thing and is a big thing in and of itself. And it doesn't need differentiability in any way, shape, or form. It is a huge and mighty thing in and of itself. And yeah, you will explore that if you go take anything which talks about more topology in general. Okay, so here are a bunch of theorems. You can try and prove these. You've basically proven this one on a test. The others are going to be are going to be new, but if you find yourself really bored, you're on a bus or something, and you want to see if you can take a shot at it, you have all the tools that you need to try and prove these theorems. Okay, otherwise that's what we'll do when we come back on Thursday. Everyone else, remember there is a test on Friday, so make sure that you prep for that. It will cover everything up to and including what we did last week, so none of this stuff, but everything right before we went on break. And yeah, that's it. Yeah. Yeah, no problem. See you, Sophia. Everyone else, yep, same thing. See you on Thursday. Have a good Wednesday, and I'll see you then.